Merhaba, this is Liam in for Bear. I typed this into Claude. When one AI checks another AI's answer, does that actually make the answer more reliable? The answer is yes, sometimes, and it depends entirely on one variable. Here's the variable. A student rereads their own exam the night before it's graded. They catch some typos. They miss the one structural error that costs them most, the same one they had going in. Stack 20 rereads, same exam, same student, same systematic miss every pass. More reviews, same blind spot, just more confident. A model checking its own reasoning is the same student. The error it structurally can't catch is the one it generates, because catching it requires seeing past the assumption that caused it. About 2/3 of self-generated errors survive self-checking, one model checking itself on the mistakes it made. Bar is illustrative, the finding is consistent. You could resample, run it 10 times, let the majority vote, but if the error is structural, a model misconception rather than a sampling artifact, the majority votes the wrong answer into consensus. Agreement isn't correctness. So you bring in a second model to check. The question that matters isn't which lab built it or what it's called. It's this: when the first model is wrong, does the second fail the same way or a different way? That's the entire question. Correlated errors, same family models trained on overlapping data with similar objectives, cluster their mistakes together. Cross-family errors scatter. The scatter is the mechanism that makes ensemble verification work. The hierarchy is monotonic and roughly this: within a single model, errors are most correlated. Same family, different models next. Cross-family least. The ordering is studied. Bar heights are illustrative. Why does same family track together? Pre-training, tokenizer, RLHF recipe. Shared pipeline means shared blind spot geometry. Different name, same training river, the errors converge. Define kappa as the probability a verifier accepts a wrong answer. Same family, kappa approaches 1, the verifier always agrees, so agreement tells you nothing. Cross family, kappa falls toward base rate. The disagreement becomes the actual signal. When it works, decorrelation. Wrong answers scatter across the output space. Right answers converge on one class. A diverse panel exploits exactly this. Wrong guesses cancel in the noise, right answers reinforce. That's the mechanism that actually works. Measure the oracle gap, how much of the possible verification gain a verifier actually captures. A same family verifier closes essentially none. A genuinely cross-family panel closes a large share. Bars are illustrative. A diverse panel reaching a verdict. The strength of this isn't the head count, it's whether the failure modes are actually independent. Pull back, the outliers cancel. The shared truth is what remains. This only holds when each member of the panel is genuinely failing differently from the others. The correction, a panel of many models collapses to roughly 3 effective independent voters. The rest are correlated enough they count fractionally. More bodies doesn't mean more information, it means more spend for diminishing returns. Different lab, different logo, that's not what you're buying. What matters is whether the error surfaces actually diverge. A model that genuinely fails differently is what the math requires. Most different families aren't that. One study showed a well-calibrated same-family verifier recovering a large share of the cross-family gain, roughly 4/5, illustrative. The family label is a rough proxy, it's not the thing itself. The disconfirming case, some studies found the most correlated pairs were cross-family, overlapping pre-training, similar alignment recipes. The branding doesn't bind. If you can't measure the actual error overlap, accept that you're guessing. 2 systems, different labs, different weights, different training runs, producing the identical wrong output. Same error. The ring draws on. This is the edge case the simple story doesn't warn you about. When more voters lose. Correlated panels fall below their own theoretical independence by roughly 8 to 22 points, illustrative. You built a panel assuming it was diverse. It wasn't, and you paid for all those calls. A single calibrated judge, not necessarily the largest model, just the most accurate for this task, can match or beat the correlated panel. You can scale voter count and get less reliability. That's the trap. The misleading tier, a correlated majority outvotes the one correct answer. Ensemble accuracy, 0. This is the failure mode that inverts the intuition. The panel assembled to improve reliability actively degrades it. A crowd confident in a wrong answer, one voice with the right one. The crowd drowns it. This is exactly what correlated majority voting does to a correct outlier. Hold on that voice unheard. The panel was supposed to surface it. It buried it instead. About 1 in 10 hard queries fails across many genuinely distinct models. That's the shared error floor. The questions every model gets wrong are outside the reach of any ensemble. You can't vote your way past a universal miss. And there's a ceiling. Serial verification, chaining model into B into C, doesn't compound reliability indefinitely. It saturates. Then past the crossover, adding more gates actively harms accuracy. More checking, worse results. That's not pessimism, it's the math. Reliability under serial verification is bounded below 1, R infinity less than 1. Two curves, accuracy gain as gates are added and the cost of those gates. They cross at crossover depth K-dagger, the point past which you are paying more and getting less accurate. Floor, ceiling, crossover, illustrative. A long cost receipt. Each verification pass costs approximately what a generation pass costs. The ceiling is finite, the receipt is not. You don't always need two. One cheap prompt marker, a token meaning wait, reconsider, cut the self-checking blind spot by roughly 9/10 inside a single model, illustrative. No second model, just a different first pass. Post-training with outcome feedback teaches intrinsic self-correction, a model learning to catch its own mistakes without a second judge. This makes some multi-model chains redundant before you even build them. The honest frame, the research on multi-model verification shows its own seams, evidence for and against, open questions, unresolved cases. Always use cross-family is a clean rule that overstates the finding. The mechanism is error surface divergence. Measure that directly. Let's recap with Claude. A second model buys reliability only if it fails differently from the first. Same family, you're resampling, not verifying. Cross-family, check actual error overlap, don't assume. A correlated majority, your single best judge may beat the whole panel. There's a shared error floor no ensemble reaches. Serial verification saturates and reverses past the crossover depth, and within model corrections can substitute for a second model entirely. Your turn, paste this into Claude. I'm building a multi-model verification step. One model generates, a second checks it. Walk me through 3 diagnostic questions before I treat this as a real reliability gain. First, how correlated are the error surfaces of these two models, based on their training lineage, not their names? Second, am I past the point where additional verification gates hurt more than they help? What's my estimated crossover depth? And third, what's the simplest within-model intervention I should try first, before adding a second model at all? Run that. The third question will tell you something most multi-model implementation guides skip entirely. Who checks the checker? Lay 'em in for bear.